Welcome to this episode of Eureka, and we are going to have a very informative conversation with Professor Bidyendu Mohan. He is an INSA honorary scientist at Vishwabharati University in Santiniketan, and he has done tremendously original work in theoretical physics and chemistry, that kind of combination. It's a very, very interesting field. We'll first look at his brief profile and continue our conversation. Keep watching Eureka.
Professor Bidyendu Mohan has been one of the early pioneers of the electron density theory of chemistry and physics of atoms, molecules and solids. His works have received spontaneous and warm applause from numerous scientists from different countries. Among them are Professor C.A. Coulson and R.P. Feynman. Presently a Professor Emeritus of Punjab University, Chandigarh and Honorary Scientist at Indian National Science Academy, New Delhi. Professor Deb has also been in respectable and responsible positions in various capacities in several national institutions. For decades, he has been well known as a highly creative and original multidisciplinary teacher and research scientist who enjoyed out-of-the-box thinking and did not accept intellectual boundaries. Born on September 27, 1942, Professor Deb did his BSc Honours and MSc in Chemistry from Calcutta University and DPhil in Mathematics from Oxford University, UK, under the supervision of Professor C.A. Coulson, Director, Mathematical Institute, Oxford University, the celebrated mathematical scientist and humanist. Professor Deb's intellectual interests include theoretical chemistry, chemical physics, atomic and molecular science, conceptual aspects of human civilization, among others. Professor Bidyendu Mohan is also well known as a scholar of literature and art of both the Eastern and Western worlds. He is perhaps the only science teacher who has been using examples of classical Indian art and for decades to illustrate and explain certain advanced concepts in science to students of BSc, MSc and PhD courses. Professor Deb has received various national and international awards. Noted among them are S.S. Bhatnagar Prize, CSIR in Chemical Sciences and Sir C.V. Raman Award in Physical Sciences.
Sir, thank you, sir, being with us. I mean, it's a great honor for us to have you in our show, and you have done very excellent work in your area. First thing that struck me when I was looking at your profile is you did mathematics, but then you are a professor of chemistry. Mathematics and chemistry is not something that people will think as something you can bridge. Sometimes people who are doing mathematics might even do theoretical physics. But how does a chemistry professor from mathematics? I mean, it's a bit curious.
Yeah, you see, my education was in chemistry. BSc and MSc was in chemistry. And because I was interested in geometry, molecular geometry, you realize that eventually is going to take me into mathematics. But in my case, this drifting into getting a doctorate in mathematics was somewhat accidental. Because I chose Professor Charles Coulson at Oxford University, and he chose me as well as my doctoral supervisor. Now, Professor Coulson was the director of the Mathematical Institute, which is the mathematical faculty in Oxford University. And since, therefore, I was directly under the mathematics faculty, and since I was a chemistry MSc, anybody who do DPhil under the mathematical faculty will have to first do a diploma in advanced mathematics. So Professor Charles Coulson and others had decided what kind of advanced level mathematics courses I should take. This is a one-year course, one-year program followed by the DPhil. So there I worked on electronic interpretation of molecular shapes. That is my doctoral thesis.
But this is your favorite work, which kind of tried to explain why a molecule takes a particular shape.
Both explain and predict. There you could easily, you see, an important job of theory is to predict.
So can I ask you a question on this? You were looking at some kind of a prediction, right? So we already know what is the shape of water molecule. So your theory kind of fits with it.
But explanation was not there.
Yeah, explanation was there, but your theory fits with it. But is there some prediction that you made which was very novel, meaning that people didn't know what it was? Yes. Your theory predicted, and then finally it also confirmed that it was.
Yes, not finally. We could. You see, I used a simple postulate. You see, if you have a number of molecular orbitals, this is an approach without any calculation. Because this was done after my return from Oxford. I was jobless. India did not have any computers, worthwhile computers at that time. And I wanted to work in chemistry, which, as you implied before, mathematical expressions will not do. So minimum mathematical expressions and thinking, and I used a lot of group theory in this work, but kept it somewhat disguised so that it can appeal to the chemists. Okay, so this is without any calculations, and therefore this should be able to predict. Now, apart from one simple example of prediction was the CH2 ground state. CH2 ground state was believed to be linear. But according to my model, it should be bent.
Little bit.
Right. I could, by comparing with similar molecules, I could even come up with a bond angle.
Okay.
No calculation, no experiment. Just, looking at the density, qualitative density. Now, spectroscopically, the molecule in a ground state was found to be linear. We should realize that when you interpret experimental data, you need theory. If you do not interpret theory, data can be correct, but your conclusion
can be wrong. Yeah.
So our conclusion was this. Then very accurate quantum mechanical calculations outside India showed that it is indeed bent, and the angle is not exactly as we said. It cannot be, because that's the accurate, but it's within 4 or 5 degrees of what we had predicted.
Okay.
That satisfied us, and then the very distinguished well-known spectroscopist then re-looked at his data and said his earlier data, you see, nobody questions his data. He is such a wonderful man. His earlier data are consistent
with your prediction,
with the bent CH2.
That's a very interesting point. This is where we are going to take a very small break, but keep watching Eureka, because it's going to be very interesting. What happened when he wrote all these things and sent his paper to the journal? Let's going to look at it after a small break. Keep watching Eureka.
And India has a crucial role to play. India is the biggest member, the largest member of the Commonwealth.
Yeah.
And we want Commonwealth more than just a network of people. We want more than, heads of state getting together.
How can you be the custodian of what is happening in Syria?
We have a responsibility to our fellow human beings, no matter where they're living. Britain is a very compassionate country. We don't attack countries with a view to kill their people.
Watch an exclusive interview of Lord Dollar Popat, trade envoy of the British Prime Minister. Saturday 8:30 p.m. and Sunday 9:30 a.m. only on Rajya Sabha TV.
Welcome back to Eureka. We are having a very wonderful conversation with Professor Bidyendu Mohan, who is an honorary professor at Vishwabhat University at Santiniketan, and he has done very wonderful work on chemistry, understanding the molecular structure and so on. We were talking about how you were able to come up with a theory to understand why molecules take certain shape, or rather how they take certain shapes. I mean, people had equations which would tell you that this would be the angle, but then there was no explanation and you gave a theory, and then it also gave kind of correct results in certain chemicals for which people had some opinion, but then later after your theory it proved to be correct.
Right.
There was a very interesting incident that I came to know, that when you wrote up your paper and sent it to some frontline chemistry journal, they were very happy, right?
I wouldn't say they are happy. You see, journals don't express happiness. Okay. The editor was, again, the chief editor was a very distinguished chemist. So he sent the paper to very well-known people, obviously. I had a feeling they did not like the paper.
Why? Because it is tough? I mean, you are very mathematical that chemists cannot understand?
It had only one equation, namely the Hellman-Feynman theorem.
That's it.
The result, the force expression in molecule based on the Hellman-Feynman theorem, using only one expression. The group theory part was there, obvious but subtle. Lot of group theory. Okay, so that is a branch in abstract algebra. Now, and then the referees kept on raising objections of various kinds. The chief editor would send this back to me, this is how it goes. And I would reply to them, the referees will raise fresh objections. I could see that the chief editor obviously thinks the paper
Is worth.
Could be a significant paper. Not could be, he concluded that it's a significant paper. He would not let it go rejected like that. So he kept on, he was acting like a postman. Okay, we were fighting it out. Finally, the main referee made a mistake. He said, if what Dev says is correct, then H3O plus, namely, if you add a proton to H2O molecule, H3O plus should be pyramidal, but it is actually planar. So Dev is wrong. His entire approach is wrong. Now, you see, in mathematics, no matter how sophisticated, how involved your mathematics is, you can just show one counter example.
That's it.
Whole thing is destroyed. So he came up with a counter example. So I was very annoyed.
I'm reminded of a very interesting anecdote. Apparently, somebody wrote 100 mistakes of Einstein during Einstein's time. It seems Einstein wrote back saying that if there is only one error, that's enough to disprove. You don't need to show 100 errors.
Exactly. There are a lot of stories like this.
So continue, sir.
Yeah. So I then cited established experimental results in my reply. Say that I am quite unhappy, not only surprised but unhappy at this comment, because it has been well known that H3O plus is a pyramid.
It's a pyramid.
It's a pyramid.
Okay.
Like NH3. I told you the number of valence electrons.
Yeah.
NH3 has the same number of valence electrons as H2O plus. Oxygen has one more electron than nitrogen.
So it should be same. Yes.
Pyramidal shape. It's a so now I said. Then I said something which I should not say because I was very young.
It's okay.
I said I don't care if these papers, there were 2 papers, if these papers are not published. But nobody can make a statement that Dev has made such a silly mistake. Once this reply went, the chief editor sent me a reply, your papers are accepted. He closed the issue.
That's a very, very interesting story, and I think it tells a lot. Let me move a little bit forward. I mean, another area that you have worked is trying to look at electron as a fluid. Trying to understand the
electron
dynamics.
density as a fluid.
Yeah. So, can you explain to us what exactly you are trying to do? What kind of questions you are pondering when you are trying to build a model like that?
Yeah. You see, this brings up a point that for a basic scientist, it can be very helpful to be in an institute like IIT. Now, Professor Feynman, Richard Feynman, suggested that I should look also the question of stresses in molecules.
Okay, not only forces but also stresses.
Also stresses. Now he said he was interested in stresses at that time, but then did not publish anything on that because he got diverted into other issues. I presume the other issues are the what he received a Nobel Prize for. Okay. But in his practice, I got diverted to other issues. So I thought, since you are so much interested in forces, I thought, why not look at stresses? And he had written something on stresses, and he sent me just those unpublished notes, a few pages, Xerox copies. So I had a national talent scholar in physics, a girl, joining me at that time. So I had both physics and chemistry people in my group, and she was in the physics department. She came to me and said that I want to do work which nobody has ever thought about before.
Who is she? What's her name?
Anjali Bamzai.
Okay.
Now Bamzai is her husband's surname. She is at present director of the climate dynamics program under National Science Foundation, US.
Very good. So she came to you with saying that I want to take up a problem which nobody has looked at.
I said, I don't know if I can help you with that, but we can try. If you choose to work with me, it's entirely up to you. We can try. Then I showed her what Richard Feynman had written to me. I said, look, I have done a literature search. There is nothing on this. Nobody has done any work on this. It's just Professor Feynman's suggestion, and it is something like not even smoke. So, in this kind of work, out of thin air, we first need to create smoke.
Some structure.
Smoke, but smoke doesn't have a structure. So let smoke gradually solidify. In our mind, we will proceed so that it can gradually take shape and form probably a crystal.
That's a right idea.
Okay, so this is something we have to try to do. Now, I must tell you, I don't know if we can do that, but if Professor Feynman has suggested that, and I had actually written to Professor Charles Coulson saying that Professor Feynman has given this suggestion to me. Now, you see, stress is force per unit area.
Yeah.
So Professor Coulson wrote to me, I do not understand what new information, what new insight you will get out of just force per unit area. So he was skeptical. I was in a dilemma because on the one hand Richard Feynman, on the other hand Charles Coulson, and I had tremendous respect for his insight. And this is
Two or opposite.
contrary. So what should I do? Finally, I followed my gut feeling and went ahead with stresses. So then with Anjali Bamzai, we worked on stresses in molecules and showed that one can define a stress tensor for atoms and molecules and solids, which would have the same form as Maxwell's stress tensor for classical electromagnetic fields.
Okay.
This is the first, we were elated. Then I told Anjali, that's all very fine, it's fundamental fine. But as a chemist, I would ask myself, what good does it do? What use we are going to put this to in chemistry? So we applied this to the study of chemical bond. And that is how it went, fine. So these papers were, people like this paper. But you see, as a scientist, I have always been suspicious and very dissatisfied with my work. I said, fine. So what? Is that the end?
Yeah, that's always a question that
Is
one
that
plays.
the end? Nice papers and out of my stress papers actually it sort of led to a lot of work by other people. Still, so what? Then I said it's advantageous to be in an IIT. So IIT Bombay had a fluid dynamics group. I knew that stress tensor occurs in classical fluid dynamics, for example, the Navier-Stokes equation, which is one of the ultimate, for. Okay, so is there a Navier-Stokes equation also for electron density? Can we regard it as a fluid? Then the stress tensor is a natural thing. And that is how it turned out to be.
Let's move to the next area, which again, you may not say that it's a great work, but something that you loved. For example, creating an equation called DC equation, which can be kind of an alternative to Schrodinger's equation, which generally people use. How did you come to this idea that we need a different equation to explain something when, you know, the Schrodinger equation is kind of famous and universal?
Yeah. You see, quantum fluid dynamical equations which we obtained, incidentally I should say at this time that people watching this program should not think all this is my work. I was extremely fortunate to have a very dedicated group of bright and courageous students, PhD students, and I don't know why they came to me, but like I mentioned, Bamzai. So they came to me, and some of them said, I was very fussy that if you don't accept me, then I'm not going to do a PhD. That kind of threat. I said, okay, don't say these things, so fine, we'll proceed. So all these works, particularly stress, and some of these students became quite distinguished in their own right, and I have great respects for them. So
it's always a collective effort, yes, of course.
And because you see, after returning from Oxford, I did not do any work outside India. All the works are done entirely in India in relative isolation, because there was considerable incomprehension about theoretical chemistry in India in those days, except a few high-level scientists. Okay, even now my work probably is more appreciated by mathematicians, theoretical physicists, and engineers
Than the chemist.
Okay. So because of the quantum fluid dynamical equations contain two fundamental quantities, namely fluid density and fluid current density. And these are the two fundamental because there are two equations. One is a continuity equation, another is an equation of motion. Let's leave the details. These are the two fundamental fluid dynamical equations. Therefore, it seemed to me that if electron density obeys these, and we showed that they do, then we should use these equations to try and obtain a single equation for the direct calculation of electron density.
Okay.
Now, biochemists, including biophysicists like Professor G.N. Ramchandran, whom we hold in great esteem, had told me that if you can do that, it will tremendously help biological scientists, biochemists, because all of us are looking for such an equation, quantum mechanical equation. Professor Ramchandran himself tried to obtain this, but he was not a quantum mechanical person basically. But he realized the significance of this. So how to do that? And so then we had a bright student, another bright student. So we discussed that can you combine these two equations somehow so that they give rise to another equation,
Okay.
which has features of both, and we could obtain that. That is the Dev Chattaraj equation, Chattaraj being the PhD student. He is now a distinguished scientist. He is at IIT Kharagpur, very distinguished scientist. So Dev Chattaraj equation or DC equation. Now this, see, the fluid dynamical work brought home to me forcefully this idea that what I said a little while ago, that structure is a consequence of dynamics, that so far people have been using Schrodinger equation where time did not feature, time independent equation did not feature, to calculate electronic structures and various properties of atoms, molecules and solids. But that is not the full picture. The time dependent or the dynamical Schrodinger equation was extremely difficult to solve. People kept it aside. So therefore, instead of trying to solve that, an alternative to time dependent Schrodinger equation through this fluid dynamical equation, that is the DC equation. And in the process we used what is a very powerful technique, what is presently known as density functional theory.
Okay.
Okay. Now density functional theory began by saying from 1964 by Hohenberg and Kohn that electron density in the ground state contains all information about the system. What about excited states? Silence. That will not do. You cannot bypass Schrodinger. Wave function contains all information, not just the ground state, about all states. Okay, so we realize that you need to have both the electronic charge density and electronic current density to have a complete picture. And that
is what?
Is the DC equation.
That's a very interesting thing.
So,
now let me change the track. What ails our higher education system? What do you think we need to do so that we sustain our leadership and build forward?
First of all, we have not been leaders because we have been followers, not leaders. Now, what we need is original thinking. Original thinking for educating our young boys and girls and trying to release their minds from captivity. Let it be free flowing kind of thing. But we have been conditioned from school in thinking along a certain line, and this has been brought in by a colonial, I'm using a catchphrase, a colonial system of education, but it's absolutely correct. This system of education compartmentalizes subjects, and every subject is further compartmentalized into sub-disciplines. For example, chemistry has been traditionally compartmentalized into physical, organic, inorganic, and in the manner in which this has been done in education also, then they don't have overlap.
Everything is in silos.
Everything is in a box.
One of another area that you are fascinated, if I should say so, is trying to see connection between science, arts and literature. That's one of your favorite area. What's your reflection on that?
As I said, any field of human endeavor has structure and dynamics.
And they are related.
And they are related. It is through this concept of structure and dynamics that you can connect science, literature and art. So you need a scientific approach, same approach which you bear to examine natural phenomena, unknown problems, scientific approach to India, studying Indian culture and civilization. It is such a magnificent multidisciplinary area that it is virtually impossible for any person to do this single-handed. Yet this is what I have tried to do.
That's a very interesting point. We had a very wonderful discussion. There are a lot more to discuss, but our show time is a big constraint. We had a very wonderful talk with you, sir, and keep watching Eureka. We'll come back with a nice conversation next week.